3.3 The inverse Z-transform. In using the Z-transform for analysis of discrete time signals and systems, we must be able to move back and forth between time domain and Z-domain representations. Often, this analysis involves finding the Z-transform of sequences and, after some manipulation. 116 Chapter 3 The Z-transform of the algebraic expressions, finding the inverse Z-transform. The inverse Z-transform is the following complex contour integral, xn equals 21. 1x, z, zn 1 dz, 3.36, RRJFC, where C represents a closed contour within the rock of the Z-transform. This integral expression can be derived using the Cauchy integral theorem from the theory of complex variables. See Brown and Churchill, 2007, for a discussion of the topics of Laurent series and complex integration theorems, all of which are relevant to an in-depth study of fundamental mathematical foundations of Z-transform. However, for the typical kinds of sequences and Z-transforms that we will encounter in the analysis of discrete LTI-SY-STEMs, less formal procedures are sufficient and preferable to techniques based on evaluation of EQ. 3.36 In sections 3.3.1-3.3.3, we consider some of these procedures, specifically the inspection method, partial fraction expansion, and power series expansion. 3.3.1 Inspection method. The inspection method consists simply of becoming familiar with, or recognizing by inspection, certain transform pairs. For example, in section 3.1, we evaluated the Z-transform for sequences of the form xn equals anu n, where it can be either real or complex. Sequences of this form arise quite frequently, and consequently, it is particularly useful to make direct use of the transform pair z1 anu n plus dash dash plus isa gt lal. 3.37, 1 If we need to find the inverse Z-transform of 3.38, isilk 2x, z, 1-cl, 1 and we recall the Z-transform pair of EQ, 3.37, we would recognize by inspection the associated sequence as xn equals 0 fern. If the rock associated with x, z, in EQ, 3.38, had been isil lt, we can recall transform pair 6 in table 3.1 to find by inspection that xn equals gfunij. Tables of Z-transforms, such as table 3.1, are invaluable in applying the inspection method. If the table is extensive, it may be possible to express a given Z-transform as a sum of terms, each of whose inverse is given in the table. If so, the inverse transform, LE, the corresponding sequence, can be written from the table. 3.3.2 Partial fraction expansion. As already described, inverse Z-transforms can be found by inspection if the Z-transform expression is recognized or tabulated. Sometimes, x, z, may not be given explicitly in an available table, but it may be possible to obtain an alternative expression for x, z, as a sum of simpler terms, each of which is tabulated. This is the case for any rational function, since we can obtain a partial fraction expansion and easily identify the sequences corresponding to the individual terms. IORN section 3.3 The inverse Z-transform. To see how to obtain a partial fraction expansion, let us assume that x, z, is x. Pressed as a ratio of polynomials in ZL, LE, 0.36, GRL, 3.39, x, z, lex rise fun ins sys. Such Z-transforms arise frequently in the study of LTI systems. An equivalent expression ALU is SIF MM. KZNLB KZM, x, z, equals underscore dash k equals dash dash d underscore underscore underscore, 3.40, and zm loxn k by k equals oiezom equation, 3.40, explicitly shows that for such functions, there will be m zeros and n Larley poles at non-zero locations in the finite z-plane assuming AO, BO, and bm are non-zero. In addition, there will be either mn poles at z equals 0 if mgtn or nm zeros at z equals 0 if ngtm. In other words, z transforms of the form of EQ 3.39 always have the same 1.37 number of poles and zeros in the finite z-plane, and there are no poles or zeros at z equals 0, 0. To obtain the partial fraction expansion of x, z, in EQ 3.39, it is most convenient to note that x, z, could be expressed in the form 1.38, m1n, 1ckz, the x, z, equals bo underscore k equals dash dash l underscore underscore underscore, 3.41, 1.38, aon1n, 1 dkz, that k equals Lshin where the qs are the non-zero zeros of x, z, and the dks are the non-zero poles of x, z, mos if mltn and the poles are aliased order, then x, z, can be expressed as arm x, z, equals ln1ak, 3.42, k equals 1 obviously, the common denominator of the fractions in EQ 3.42, is the same as the Orn denominator in EQ 3.41. Multiplying both sides of EQ 3.42 by 1 dkc1, and city evaluating for z equals colon, dk shows that the coefficients, ak, can be found from door any, 3.43, entify. Example 3.92 ND order Z transform. Consider a sequence X New Jersey with Z transform 1 1 X, Z, 3.44, is ILK 2, 1, ZL, L is L, the pole 0 plot for X, Z, is shown in figure 3.10. From the Rock and Property 5, section 3.2, we see that X New Jersey is a right-sided sequence. Since the poles are both 1 st order, x, z, can be expressed in the form of EQ 3.42, i.e., LA2x, z, equals, plus dash dash 1 dash E1, 1, E1 from EQ 3.43, al, 1 dash, ZL, x, z, j, 141 Z1. I equals minus 1, 42 equals 1 slash 4, 1 LE1, 1, Z1, Z equals 1 slash 441 minus 1, 2 ZIA2, 1 dash, ZL, X, Z, I, 1 equals 2 2 Z equals 1 slash 2, LLE1, 1, E1, 2 equals 1 slash 2, observe that the common factors between the numerator and denominator must be cancelled before evaluating the above expressions for L and A2, therefore, minus 1 2x, Z, equals plus 1 L, L dash L, since x and L is right-sided, the rock for each term extends outward from the outermost pole. From table 3.1 and the linearity of the Z transform, it then follows that xn equals 2 gru n dash, rarn. Figure 3.10 pole 0 plot and rock for example 3.9. Section 3.3 The inverse Z transform. Clearly, the numerator that would result from adding the terms in EQ 3.42 would be at most of degree n1 in the variable ZL. If m colon colon n, then a polynomial must be added to the right-hand side of EQ 3.42, the order of which is mn. Thus, for m colon colon n, the complete partial fraction expansion would have the form mnnx, z, equals lbrzr plus l dash 1 underscore a underscore k dash 3.45, r equals ok equals l if we are given a rational function of the form of EQ 3.39, with m colon colon n, the BRS can be obtained by long division of the numerator by the denominator, with the division process terminating when the remainder is of lower degree than the denominator. The AX can still be obtained with EQ 3.43. If x, z, has multiple order poles and m colon colon n, EQ 3.45 must be further modified. In particular, if x, z, has a pole of order s at zd and all the other poles are 15t order, then EQ 3.45 becomes mnnascx, z, equals lbrzr plus l.1 underscore dz1 plus l, 1m, 3.46, r equals ok equals lk hashtag 1m equals l. The coefficients ak and by are obtained as before. The coefficients cm are obtained from the equation cm equals dash, s underscore 1 dash dot. sm dash d underscore s dash underscore m, 1 dw, sx, w1, underscore. 3.47, m dot c dw equals d, 1 equation, 3.46, gives the most general form for the partial fraction expansion of a rational z-transform expressed as a function of zl for the case m::n and for d a pole of order s. If there are several multiple order poles, then there will be a term like the third sum in EQ, 3.46, for each multiple order pole. If there are no multiple order poles, EQ, 3.46, reduces to EQ, 3.45. If the order of the numerator is less than the order of the denominator, MLTN, then the polynomial term disappears from X. 3.45, and 3.46, leading to EQ, 3.42. It should be noted that we could have achieved the same results by assuming that the rational z-transform was expressed as a function of z instead of zl. That is, instead of factors of the form, 1az1, we could have considered factors of the form, za. This would lead to a set of equations similar in form to x. 3.41, 3.47, that would be convenient for use with a table of z-transforms expressed in terms of z. Since we find it most convenient to express table 3.1 in terms of, the development we pursued is more useful to see how to find the sequence corresponding to a given rational z-transform. Let us suppose that x, z, has only one st order poles, so that EQ, 3.45, is the most general form of the partial fraction expansion. To find xn, we first note that the z-transform operation is linear, so that the inverse transform of individual terms can be found and then added together to form xn. The terms brzr correspond to shifted and scaled impulse sequences, i.e., terms of the form bro nrj. The fractional terms correspond to exponential sequences. To decide whether a term 1. Chapter 3 The z-transform corresponds to dk, nu n or dash, flu n-1, we must use the properties of the rock that were discussed in section 3.2. From that discussion, it follows that if x, z, has only simple poles and the rock is of the form RRLTIZLTRL, then a given pole dk will correspond to a right-sided exponential, dk, nun if it RR, and it will correspond to a left-sided exponential if I don't know I2, RL. Thus, the rock can be used to sort the poles, with all poles inside the inner boundary RR corresponding to right-sided sequences and all the poles outside the outer boundary corresponding to left-sided sequences. Multiple order poles also are divided into left-sided and right-sided contributions in the same way. The use of the rock in finding inverse z-transforms from the partial fraction expansion is illustrated by the following examples. Example 3.10 Inverse by partial fractions. To illustrate the case in which the partial fraction expansion has the form of EQ, 3.45, consider a sequence xn with z-transform 1 plus c1, 2x, z, equals, isl gt1. 3.48, 1. L-CL, 1CL, the pole 0 plot for x, z, is shown in figure 3.11. From the rock and property 5, section 3.2, it is clear that xn is a right-sided sequence. Since m equals n2 and the poles are all ist order, x, z, can be represented as al plus x, z, eo plus 1 minus 1 1 underscore 1 dash 2 z. The constant eo can be found by long division, 2 plus 1 dash 2 plus 2 z 1 plus 1 z 2 dash 3 z 1 plus 2 5, colon dash 1 minus 1. Since the remainder after one step of long division is of degree 1 in the variable c1, it is not necessary to continue to divide. Thus, x, z, can be expressed as -1 plus 5c1x, z, 3.49, 2 plus, 117 to 1. 2, 1c1. LRM Section 3.3, CNLY8 to all healer he list 15, R5, the T9, the inverse Z-transform figure 3.11 pole 0 plot for the Z-transform in example 3.10. Now the coefficients A1 and AZ can be found by applying EQ, 3.43, to EQ, 3.48, or, equivalently, EQ, 3.49. Using EQ, 3.49, we obtain therefore, 98x, z, equals 21 colon, plus 1 z 1. 3.50, from table 3.1, we see that since the rock is IGT1, Z2 plus 28 New Jersey, 11 Z-1 plus plus UNJ1C. Thus, from the linearity of the Z-transform, 1, 11xn equals 28n 9 2 ERN plus 8 ERN. In section 3.4, we will discuss and illustrate a number of properties of the Z-transform that, in combination with the partial fraction expansion, provide a means for determining the inverse Z-transform from a given rational algebraic expression and associated rock, even when x, z, is not exactly in the form of EQ, 3.41. The examples of this section were simple enough so that the computation of the partial fraction x expansion was not difficult. However, when x, z, is a rational function with high-degree polynomials in numerator and denominator, the computations to factor the denominator and compute the coefficients become much more difficult. In such cases, software tools such as MATLAB can implement the computations with ease. 3.3.3 Power series expansion. The defining expression for the Z-transform is a Laurent series where the sequence values xn are the coefficients of n. Thus, if the Z-transform is given as a power series in the form x, z, equals L00 xn zn, 3.51, n equals -x, equals, plus x-2z2 plus x-1z plus xo plus x1c1 plus x2e2 plus, we can determine any particular value of the sequence by finding the coefficient of the appropriate power of. We have already used this approach in finding the inverse transform of the polynomial part of the partial fraction expansion when m, and this approach is also very useful for finite length sequences where x, z, may have no simpler form than a polynomial in ZL. Example 3.2 Finite length sequence. Suppose x, z, is given in the form x, z, equals z2, 1 z1, 1 plus z1, 1 z1. 3.52, although x, z, is obviously a rational function of z, it is really not a rational function in the form of EQ, 3.39. Its only poles are at z0, so a partial fraction expansion according to the technique of section 3.3.2 is not appropriate. However, by multiplying the factors of EQ, 3.52, we can express x, z, as 1 x, z, z2 underscore colon, z1 plus 2. Therefore, by inspection, xn is seen to be 1, n minus 2, n equals -1, xn 1 to 1, n 0, 1 n equals 1, 2 feet 0 inches, otherwise. Equivalently, 1 xn equals on plus 2 zaln plus 1 on plus zaln 1. Section 3.3 The inverse Z-transform. In finding Z-transforms of a sequence, we generally seek to sum the power series of EQ, 3.51, to obtain a simpler mathematical expression, example a rational function. If we wish to use the power series to find the sequence corresponding to a given x, z, expressed in closed form, we must expand x, z, back into a power series. Many power series have been tabulated for transcendental functions such as log, sin, etc. In some cases, Such power series can have a useful interpretation as Z-transforms, as we illustrate in example 3.12. For rational Z-transforms, a power series expansion can be obtained by long division, as illustrated in example 3.13. Example 3.12 Inverse transform by power series expansion. Consider the Z-transform x, z, log, 1 plus a z1, is gt lal, 3.53, using the Taylor series expansion for 10g, 1 plus x, with ixllt1, we obtain 0 0, l, n plus 1 and n z x, z, equals l n n equals l. Therefore, in plus l and x n equals, minus 1, dash, n2, 1, 3.54, 0, ns, 0. When x, z, is the ratio of polynomials, it is sometimes useful to obtain a power series by long division of the polynomials. Example 3.13 Power series expansion by long division. Consider the Z-transform x, z, gt lal, 3.55, laz1. Since the rock is the exterior of a circle, the sequence is a right-sided one. Furthermore, since x, z, approaches a finite constant as z approaches infinity, the sequence is causal. Thus, we divide, so as to obtain a series in powers of zl, carrying out the long division, we obtain 1 or 1 hence, xn anu n. 124 Chapter 3 The I transform by dividing the highest power of C1 in the denominator into the highest power of the numerator. In example 3.13, we obtained a series in. An alternative is to express the rational function as a ratio of polynomials in Z and then divide. This leads to a power series in Z from which the corresponding left-sided sequence can be determined. 3.4 Z-transform properties. Many of the mathematical properties of the Z-transform are particularly useful in studying discrete